Next transformation is called reflection. Suppose the graph of the function y equal to f of x is known. To graph the function y equal to f of negative x, if we try to graph the function y equal to f of negative x based on the graph y equal to f of x, we flip the graph of y equal to f of x over the y-axis. If we make x negative, we flip the graph over the y-axis. If we make x negative, flip the graph over the y-axis. To graph the function y equal to negative f of x, if we try to graph the function y equal to negative f of x based on the graph y equal to f of x, we flip the graph y equal to f of x over the x-axis, which means if I make the entire function negative, I flip the function over the x-axis. So if the negative sign is next to x, we flip the graph over the y-axis. If negative sign is in front of the entire function, flip the graph over the x-axis. That's called reflection. If negative sign is next to x, flip the graph over the y-axis. If negative sign is in front of the entire function, flip the graph over the x-axis. Now let's look at an example here. Suppose the graph of the function y equal to f of x is given. Graph of the function y equal to f of negative x and y equal to negative f of x. Suppose this graph is given. The graph y equal to f of x is given. Graph of the functions y equal to f of negative x and y equal to negative f of x. If negative sign is next to x, if the negative sign is next to x, by the rule here, we flip the graph over the y-axis. So for the graph y equal to f of negative x, flip the graph over the y-axis. If I flip this graph over the y-axis, this point on the y-axis stays the same. This point, positive 2 here become negative 2. At this point, x coordinate is 1. If I flip over the y-axis, positive 1 become negative 1. So flip this point over the y-axis, like this point here. That's the mirror image. Then once we get 3 points, we can sketch the graph based on these 3 points. So here I flip this graph over the y-axis. That's the graph of the function y equal to f of negative x. I flip this graph over the y-axis. That's the graph of the function y equal to f of negative x. Now, how about the graph of the function y equal to negative f of x? If negative sign is in front of the entire function, flip the graph over the x-axis. If negative sign is in front of the entire function, flip the graph over the x-axis. So, in order to graph the function y equal to f of x, y equal to negative f of x, flip the original graph over the x-axis. So, if I flip this point over, positive 1 become negative 1. If I flip this point over, positive 1 become negative 1. And this point, y coordinate is 2. If I flip over, it becomes negative 2. This point, y coordinate is 2. If I flip over, it becomes negative 2. And this point, located on the x-axis. When I flip it, it stays the same. This point located on the x-axis. When I flip the graph over the x-axis, this point stays the same. Once we know these 3 points, we can sketch the graph based on these 3 points. So that's the graph y equal to negative f of x. So when I make the function negative, if the negative sign is in front of the function, I flip the graph over the x-axis. But if the negative sign is next to x, I flip the graph over the y-axis. Next, let me introduce vertical stretching and shrinking. Suppose the graph of a function y equal to f of x is known. Let c be a positive number. To graph the function y equal to c times f of x, when we have c times f of x, if c is more than 1, stretch the graph of the function y equal to f of x vertically by the factor of c. When we have c times the function, if c is more than 1, we stretch the graph vertically by the factor of c. And to graph the function y equal to c times f of x, if c is less than 1, shrink the graph of the function y equal to f of x vertically by the factor of c. So if c is less than 1, we shrink the graph vertically by the factor of c. So when we have a number c multiplied to the function f of x, if c is more than 1, we stretch the graph vertically by the factor of c. If c is less than 1, we shrink the graph vertically by the factor of c. That's called vertical stretching and shrinking. Next, let me show you an example. Suppose the graph of the function y equal to f of x is given below. Graph the functions y equal to 3 times f of x and y equal to half of f of x based on the given graph. So that's the given graph y equal to f of x. We try to graph the function y equal to 3 times f of x and y equal to half times f of x. This is kind of first function y equal to 3 times f of x. When we have a number times the function f of x, if this number is more than 1, we stretch the graph vertically by the factor of this number. Here this number is 3. So for the function y equal to 3 times f of x, we stretch the graph vertically by the factor of 3. Stretch the graph y equal to f of x vertically by 3. Stretch the graph vertically by the factor of 3. So how do we stretch it vertically? Stretch the graph vertically. Pull the graph up vertically. Pull the graph up vertically by the factor of 3. So this point is number 1. If I stretch it up by a factor of 3, means I multiply this number by 3. 1 times 3 becomes 3. So this point will be pulled here. 1 times 3 is 3. And this point here, the y-coordinate is 2. The y-coordinate is 2. If I stretch it vertically by a factor of 3, 2 times 3 is 6. This point come here. That's the first point, that's the second point. At this point, the y-coordinate is 0. At this point, the y-coordinate is 0. 0 times 3 stays at 0. At this point, the y-coordinate is 0. 0 times 3 stays at 0. So that's the graph of the function y equal to 3 times f of x. I stretch this graph vertically by the factor of 3. So 1 times 3, at this point the y-coordinate is 1. 1 times 3 is 3. At this point the y-coordinate is 2. 2 times 3 is 6. So this point go up to 6. At this point the y-coordinate is 0. 0 times 3 is 0. So it stays at 0 here. Next, how about this function y equal to half of f of x? Y equal to half of f of x. If the factor in the front is less than 1, if the number in the front is less than 1, we shrink the graph y equal to f of x vertically by the factor of half. Here, shrink the graph vertically by half. So at this point, the y-coordinate is 1. If I shrink it by a half, 1 times half is half. So this point go to half. If I shrink it by a half, 1 times half is half. At this point, the y-coordinate is 2. Half of 2, 2 times half. Since we shrink the graph vertically by half, 2 times half is 1. So this point will be here. At this point, the y-coordinate is 0. Half of 0 is 0. So this point stays here. Connect these 3 points, we can make a graph. So that's the graph of the function y equal to half of f of x. So from the graph of the function, we shrink the graph of the function y equal f of x vertically by the factor of half. Shrink by half means I multiply the y coordinate by half. At this point, y coordinate is 1. 1 times half is half. At this point, y coordinate is 2. 2 times half is 1. At this point, y coordinate is 0. 0 times half is 0. Then connect these 3 points, you can make a graph. So that's the graph of the function y equal to half of f of x. So when we have a number times the function, if the number in the front is more than 1, we stretch the graph vertically by the factor in the front. If the number in the front is less than 1, we shrink the graph vertically by the factor in the front. That's called vertical stretching and shrinking. Next transformation is called horizontal stretching and shrinking. Suppose the graph of the function y equal to f of x is known. Let c be a positive number. To graph the function y equal to f of cx, if c is more than 1, stretch the graph of the function y equal to f of x horizontally by the factor of 1 over c. When we have a c times x, here c is next to x. If c is more than 1, we shrink the graph horizontally by the factor of 1 over c. If c is more than 1, we shrink the graph by the factor of 1 over c. So it's the opposite. For vertical stretching and shrinking, if c is more than 1, we stretch the graph by c. But for horizontal stretching and shrinking, if c is more than 1, we shrink the graph horizontally by the factor of 1 over c. We use the reciprocal. Take 1 over c, then shrink the graph horizontally. And to graph the function y equal to f of cx, when we have c times x, if c is less than 1, we stretch the graph of the function y equal to f of x horizontally by the factor of 1 over c. So if c is less than 1, we stretch the graph horizontally by the factor of 1 over c. So for horizontal stretching and shrinking and vertical stretching and shrinking, it's an opposite. For vertical stretching and shrinking, if c is more than 1, we stretch the graph vertically by the factor of c. If c is less than 1, we shrink the graph vertically by the factor of c. But for horizontal stretching and shrinking, it's different. When we have a c times x, if c is more than 1, shrink the graph. If c is more than 1, shrink the graph by the factor of 1 over c. But if c is less than 1, stretch the graph horizontally by the factor of 1 over c. So for horizontal stretching and shrinking, c is next to x. For vertical stretching and shrinking, c is in front of the function. So that's the difference. And also it's an opposite. For vertical stretching and shrinking, if c is more than 1, we stretch the graph. If c is less than 1, we shrink the graph. For horizontal stretching and shrinking, if c is more than 1, we shrink the graph. And if c is less than 1, we stretch the graph. And for horizontal stretching and shrinking, we use the factor 1 over c. That's called horizontal stretching and shrinking. Next, let me show you an example. Suppose the graph of the function y equal to f of x is given below. Graph the functions y equal to f of 2x and y equal to f of 1/3 of x based on the given graph. That's the given graph. We try to graph the function y equal to f of 2x and y equal to f of 1/3 of x. Here, how do we graph the function y equal to f of 2x? Since we have a number multiplied to x, if this number is more than 1, we shrink the graph horizontally by the factor of 1 over the number. So here, 2 is more than 1, so we shrink the graph by the factor of 1 over 2. So for this graph, we will shrink the graph y equal to f of x horizontally by the factor of 1 over 2. So shrink the graph horizontally by the factor of 1 over 2. Look at this point here. At this point here, the x coordinate is 2. Since we shrink horizontally by half, 2 times half is 1. This point come here. This point come here. After swing the graph, this point come here. How about this point here? At this point, the y coordinate, s coordinate is 1. At this point, the s coordinate is 1. If we shrink horizontally by a half, 1 times half is half. So half is here. This point come here. This point come here. This point come here. Shrink by half. Shrink horizontally by half. And at this point, s coordinate is 0. 0 times half is 0. So this point stays the same. At this point, the s coordinate is 0. 0 times half is 0. So at this point, s coordinate stays the same. Then connect these 3 points. Connect these 3 points. We have a graph. So this is the graph of the function y equal to f of 2x. This is the graph of the function y equal to f of 2x. Now, how do we graph the function y equal to f of 1/3 of x? Here we have 1/3 times x. If the number in front of x is less than 1, we stretch the graph horizontally. So here, the number in front of x is less than 1. We stretch the graph horizontally. Stretch the graph y equal to f of x horizontally. By the factor of, in general, if there's a c, we stretch horizontally by the factor of 1 over c. Here we have 1/3 here. Then we do 1 over 1/3. 1 over 1/3, if we simplify, 1 over 1/3 can be rewritten as 1 times the reciprocal, which is 3 over 1. 1 times 3 over 1 is 3. So 1 over 1/3 is 3. So here we stretch the graph horizontally by the factor of 3. Stretch the graph horizontally by the factor of 3. 1 over 1/3 is 3. So stretch the graph horizontally by the factor of 3. So stretch horizontally by the factor of 3. Look at the original graph here. This point is 2. If I stretch it horizontally by a factor of 3, 2 times 3 is 6. So this point come here. At this point, the s coordinate is 1. At this point, s coordinate is 1. If I stretch it horizontally by 3, 1 times 3 is 3. So this point come here. 1 times 3 is 3. So this point come here. Now this point. At this point, the s coordinate is 0. 0 times 3 is 0. So this point stays the same. Then once we have these 3 points, connect 3 points, we can make a graph. Connect these 3 points, we can make a graph. So this is the graph of the function y equal to f of 1/3 of x. That's the graph of the function y equal to f of 1/3 of x. That's the graph of the function. So when we have y equal to f of some number times x, f of some number times x, if a number in front of x is more than 1, we shrink the graph by the factor of the reciprocal. If a number in front of x is less than 1, we stretch the graph horizontally by the factor of the reciprocal of this number. So that's the horizontal stretching and shrinking. Next, let's look at an example here. Suppose the graph of the function y equal to f of x is given below. Graph each of the following functions based on the given graph. So let's do part A first. Graph the function y equal to f of s plus 4 plus 2. When I add 4 to x, I shift the graph 4 units to the left. And then when I add 2 to the function, I shift the graph 2 units upward. So for part A, it takes 2 steps. First of all, I shift the graph 4 units to the left. When I add 4 to x, I shift the graph 4 units to the left. So let me shift this point 4 units to the left. For this point, s coordinate is 0. If I shift it 4 units to the left, 1, 2, 3, 4, the new s coordinate is -4. So that's the first point. Next point, the s coordinate is 1. If I shift it 4 units to the left, 1, 2, 3, 4, it becomes -3. Next point, the x coordinate is 3. If I shift it 4 units to the left, 1, 2, 3, 4, it becomes -1. Then connect these points, we can make the graph. That's the graph y equal to f of x plus 4. When I add 4 to x, I shift the graph 4 units to the left. Next, when I add 2 to the function, I shift the graph 2 units upward. So shift this graph 2 units upward. For the first point, y coordinate is 2. If I shift it 2 units upward, it's here, it becomes 4. For the second point here, the y coordinate is 0. If I shift it 2 units upward, it becomes 2. That's the second point. And then for the third point, if I shift it 2 units upward, the y coordinate is 1. If I shift it 2 units upward, it becomes 3. Then connect these 3 points, we can make a graph. So that's the graph. Y equal to f of s plus 4, then plus 2. That's an answer to part A. That's an answer to part A. We first of all shift the graph 4 units to the left, and then shift it 2 units upward. When I add 4 to x, I shift the graph 4 units to the left, and then when I add 2 to the function, I shift the graph 2 units upward. That's an answer to part A. Part B, y equal to negative f of x minus 2. Y equal to negative f of x minus 2. So when I make the function negative, I flip the graph over the x-axis. When I make the function negative, I flip the graph over the x-axis. When I flip the graph over the x-axis, this point is positive 2. If I flip over, it becomes -2. This point located in the x-axis, so it stays there. This point located in the x-axis, so it stays there. For this point, the y coordinate is 1. If I flip over an x-axis, it becomes -1. For this point, the y coordinate is 1. If I flip over an x-axis, it becomes -1. So those are the 3 points here. Connect 3 points, we can make a graph. So I flip this graph over an x-axis. That's the graph y equal to negative f of x. Next, when I subtract 2 from x, I shift this graph 2 units to the right. When I subtract 2 from x, I shift this graph 2 units to the right. Let me label this function here. That's the graph y equal to negative f of x. Next, when I subtract 2 from x, I shift this graph 2 units to the right. When I subtract 2 from x, I shift this graph 2 units to the right. So this point, x coordinate is 0. If I shift it 2 units to the right, x coordinate becomes 2. That's the first point. This point come here. Next, I shift the second point 2 units to the right. The x coordinate here is 1. If I shift it 2 units to the right, it becomes 3. Then for this point, x coordinate is 3. If I shift it 2 units to the right, it becomes 5. That's the third point. So connect these 3 points. Connect these 3 points. This is the graph y equal to negative f of x minus 2. That's an answer to part B. This graph is answer to part B. We first of all flip the graph over an x-axis. I got this graph. And then shift this graph 2 units to the right. This graph, that's an answer to part B. Now, for part C, we have y equal to 2 times f of x minus 3. Let me draw another graph. Let me copy function f here. Function f, let me copy function f first. That's the graph y equal to f of x. That's function f. Now for part c, we have 2 times f of x minus 3. When I multiply the function by 2, I stretch the graph vertically by a factor of 2. When I multiply the function f by 2, I stretch the graph vertically by a factor of 2. And then, when I subtract the function by 3, I shift the graph 3 units downward. So I first of all stretch the graph by a factor of 2, and then shift the graph 3 units downward. Let me first of all stretch the graph vertically by a factor of 2. So I try to stretch the graph vertically by a factor of 2. Stretch the graph vertically. At this point, the y-coordinate is 2. If I stretch the graph by a factor of 2, 2 times 2 is 4. So I shift this point here. At this point, the y-coordinate is 0. 0 times 2 is 0, so it stays here. The second point stays here. For the third point, the y-coordinate is 1. For the third point here, y-coordinate is 1. If I stretch this point vertically by a factor of 2, 1 times 2 is 2. So this point comes here. That's the graph after stretching. Y equals 2 times f of x. That's the graph after stretching. I stretch its graph vertically. Pull both points upward. I stretch its graph vertically. That's the graph y equals to 2 times f of x. Next, when I subtract 3 from the function, I shift this graph 3 units downward. Next, when I subtract 3 from its function, I shift this graph 3 units downward. We have 3 points here. Let me shift each point 3 units downward. First point is 4. If I shift it downward by 3 units, it's here. That's the first point. 1, 2, 3. I shift it downward by 3 units. At this point, y-coordinate is 0. If I shift it downward by 3 units, 1, 2, 3 is here. That's the second point. The third point, y-coordinate is 2. I shift it downward by 3 units. 1, 2, 3 is here. So, first point, second point, third point. Connect the points, we have the graph. That's the graph y equal to 2 times f of x minus 3. That's the answer to part C. This graph is the answer to part C. I first of all stretch function f vertically by a factor of 2. I first of all stretch the graph vertically by a factor of 2. And then when I subtract 3, I shift the graph 3 units downward. So that's the answer to part C. This is the answer to part C. For part D, we have f of negative x plus 3. F of negative x plus 3. When I make x negative, I shift the graph over the y-axis. When I make x negative, I shift the graph over the x-axis. This is function f. When I make x negative, I shift this graph over the x-axis, sorry, over the y-axis. When I make x negative, I shift this graph over the y-axis. So if I shift the graph over the y-axis, this point located in the y-axis, so it stays the same. It stays the same. This point located in the y-axis. At this point, x coordinate is 1. If I shift it over the y-axis, positive 1 becomes negative 1. So first point, Second point, that's the second point. For the third point, x coordinate is 3. If I shift it over the y-axis, positive 3 becomes negative 3 is here. If I shift this point over, it's here. Shift this point over the y-axis, it's here. X coordinate is positive 3. If I shift over, it becomes negative 3. Then connect these 3 points. That's the graph y equal to f of negative x. When I make x from positive to negative, I shift the graph over the y-axis. So this point stays the same. For this point, positive 1 becomes negative 1. And for this point, if I shift over, positive 3 becomes negative 3. So that's a reflection over the y-axis. That's a reflection over the y-axis. Next, when I add 3 to the function, I shift this graph 3 units upward. When I add 3 to the function, I shift this graph 3 units upward. So at this point, y coordinate is 2. If I shift it upward by 3 units, 1, 2, 3, it becomes 5. This point, y coordinate is 0. If I shift up by 3 units, 1, 2, 3, it becomes 3. That's the second point. The third point, y coordinate is 1. If I shift it upward by 3 units, I get 1, 2, 3 here. The y coordinate becomes 4. So those are new points. Then connect this point, we can make the graph. Connect these points, we can make the graph. That's the graph of the function y equal to f of negative x plus 3. That's the answer to part D. This graph is the answer to part D. So I first of all make the function like x negative. I flip the graph over the y-axis. Flip this graph over the y-axis. I get this graph. And then when I add 3 to the function, I shift this graph 3 units upward. So that's the answer to part D. Part E, y equal to f of half of x minus 2. Let me draw another axis. Let me draw another xy plane. Let me copy function f. Let me copy this function f. That's the graph of function f. That's the graph of function f. When I multiply x by a half, since half is less than 1, we stretch the graph horizontally by a factor of 1 over a half, which is 2. So when I multiply x by a half, half is less than 1, so we stretch the graph vertically, horizontally. Half is less than 1, so we stretch the graph horizontally by a factor of 1 over a half. 1 over a half is 2. So stretch the graph horizontally by a factor of 2. First of all, when I multiply x by a half, I stretch the graph horizontally by a factor of 2, because 1 over a half is 2. So if I stretch the graph, at this point, x coordinate is 3. If I stretch this point by a factor of 2, 3 times 2 is 6. So this point come here. This point x coordinate is 1. If I stretch this point horizontally by a factor of 2, 1 times 2 is 2. This point come here. That's the second point. For the third point, x coordinate is 0. 0 times 2 stays at 0. So this point stays the same. Connect all these points together. That's the graph. Y equal to f of half x. That's a horizontal stretching. Plot this graph, make it twice longer. Point endpoint, make it twice longer. So if we multiply x by some number, if this number is less than 1, we stretch the graph. If this number is more than 1, we shrink the graph horizontally. So be very, very careful. For horizontal stretching and shrinking, if a number in front of x is greater than 1, we shrink the graph. If a number in front of x is less than 1, we stretch the graph. Always shrink or stretch the graph by a factor of 1 over c. That means 1 divided by this number. Take 1 divided by this number. Here, 1 divided by a half is 1 times 2 over 1, which is 2. That's why I stretch the graph horizontally by a factor of 2, because 1 over half is 2. So stretch this graph horizontally by a factor of 2. Next, when I subtract 2 from the function, I shift this graph 2 units downward. So when I subtract 2 from the function, I shift this graph 2 units downward. If I shift this graph 2 units downward, this point is 2. If I shift it 2 units downward, it becomes 0. At this point, if I shift the graph 2 units downward, it's here. At this point, if I shift it 2 units downward, it's here. Then connect these 3 points. That's the graph y equal to f of half x minus 2. That's an answer for part E. This graph is an answer to part E. I first of all stretch the graph horizontally by a factor of 2, and then I shift the graph 2 units downward. I shift the new graph 2 units downward. That's an answer for part E. Part F, half of f of x minus 4. Part F, y equal to half of f of x minus 4. So when I multiply the function by half, I shrink the graph vertically by a factor of half. When I multiply the function by half, I shrink the graph by a factor of half. To avoid confusion, let me draw another picture. Function f is this graph. Let me copy it here. That's function f. When I multiply function f by half, function f by half, I shrink the graph vertically by a factor of half. Shrink this graph vertically by a factor of half. At this point, y coordinate is 2. If I shrink it by half, 2 times half is 1. So this point come here. At this point, y coordinate is 0. 0 times half is 0. So this point stays here. At this point, the y coordinate is 1. 1 times half is half. So this point is here. Then connect these 3 points. connect these 3 points. That's a new graph. This is a new graph. Y equal to half of f of x. This is the new graph. Y equal to half of f of x. Next, when I subtract 4 from x, I shift the graph 4 units to the right. When I subtract 4 from x, I shift the graph 4 units to the right. So shift this new graph 4 units to the right. At this point, y coordinate is 0, x coordinate is 0. If I shift it 4 units to the right, 1, 2, 3, 4, it becomes 4. This point, x coordinate is 1. If I shift it 4 units to the right, 1, 2, 3, 4, x coordinate becomes 5. That's the first point, and that's the second point. For the third point, x coordinate is 3. If I shift it 4 units to the right, 1, 2, 3, 4, it's here. It'll be here. Then connect these points, we can make a new graph. That's the graph. Y equal to half of f of x minus 4. That's an answer to part F. This graph is the answer to part F. I first of all shrink the graph vertically by a factor of half. And then when I subtract 4 from x, I shift this graph 4 units to the right. I shift the new graph 4 units to the right. Shift the new graph 4 units to the right. That's the answer to part F. Next example, graph each of the following functions using transformations. Label the X and Y intercepts and find all asymptotes if possible. Part A, f of x equal to x minus 3 squared. How do we graph this function? In order to graph this function using transformation, we need to memorize some special functions. So memorize the graph of some special functions. Power functions, absolute value functions, reciprocal functions, and root functions. Memorize the graph of some of these special functions. Now, this function here, f of x equal to x minus 3 squared. It looks like this function, f of x equal to x squared. So let's choose this function as our parent function. We take this function as a reference. So we call this function the parent function. Y equal to x squared. Let's call this function parent function. We use this function as a reference to graph this function. So let's call this function a parent function. And we need to memorize the graph of a parent function. The graph of a function y equal to x squared looks like this. It's a parabola. Now, based on this function here, how do we graph this function? If we compare this function and this function, we can see that we subtract 3 from x. So if I subtract 3 from x, I shift the graph 3 units to the right side. If I subtract 3 from x, I shift this graph 3 units to the right side. So I shift the graph 3 units to the right. If I shift this graph 3 units to the right, it was 0 here. If I shift it 3 units to the right, it'll be here. It'll be 3 here. It was 0 here. If I shift it 3 units to the right, it'll be 3 here. And the graph stays the same. Next, label the X and Y intercepts. Here we know the X-intercept is 3. What's the Y-intercept here? In order to find a y-intercept, we set s equal to 0. For y-intercept, we set s equal to 0. For y-intercept, we set s equal to 0. If I plug in 0, f of 0 equal to 0 minus 3 squared. 0 minus 3 is negative 3. Negative 3 squared is positive 9. So that's the y-intercept. 0, 9. So the y-intercept is 9 here. That's a graph. That's a graph of this function, f of x equal to x minus 3 squared. Part B. How do we graph the function f of x equal to absolute value of x minus 2? So first step, we need to choose a pattern function. Let's choose a pattern function first. In general, when we try to pick the pattern function, we drop all the numbers. If we drop all the numbers, we get a function f of x equal to x equal to absolute value of x. So we can consider absolute value of x as a pattern function. If we drop all the numbers, we have f of x equal to absolute value of x. So we can choose this function as a pattern function. That means I take this function as a reference, and based on this function, I graph this function here. So here the pattern function is f of x equal to absolute value of x. Its graph is a V shape. We need to memorize the graph of all these special functions. We need to memorize all these special functions. So the graph of absolute value of x is a V shape. That's a graph of the pattern function. We use this graph as a reference. We use this graph as a reference. Now, when I subtract 2 from the function, I shift the graph 2 units downward. When I subtract 2 from the function, I shift the graph 2 units downward. Shift this graph 2 units downward. For absolute value of x minus 2, I shift this graph 2 units downward. When I subtract 2 from the function, I shift this graph 2 units downward. It was 0 here. If I shift the graph 2 units downward, this point becomes negative 2. This point was 0 here. If I shift it 2 units downward, it becomes negative 2 here. That's the y-intercept. What's the s-intercept here? That's the y-intercept. What's the s-intercept? In order to find the s-intercept, we set y equal to 0. So for s-intercept, we set y equal to 0. If I set y equal to 0, I have 0 equal to absolute value of x minus 2. We try to get x by itself. We try to get s by itself. Here I can add 2 to both sides. I get 2 equal to absolute value of x. Add 2 to both sides. I get 2 equal to absolute value of x. If 2 equal to absolute value of x, that means s could be either positive 2 or negative 2. If absolute value of x equal to 2, that means inside x could be either positive or negative 2. So the s-intercept is positive 2 and negative 2. That's negative 2, that's positive 2. That's an s-intercept, that's an y-intercept. That's an answer to this question. That's a graph of this function. Next. Graph of the function f of x equal to 1 over s plus 2 plus 1. Graph of the function f of x equal to 1 over s plus 2 plus 1. First step, let's choose a parent function. It looks like if we drop all the numbers, it looks like this function, an hyperbola. So we can use this function as a parent function. Let me take this function as a reference. Based on this function, graph function f here. So here, for the parent function, we choose y equal to 1 over x. Choose y equal to 1 over x as a parent function. We need to memorize the graph of all those special functions. That's the graph of the parent function. For this parent function, we have two asymptotes. This line is the vertical asymptote, and this line is the horizontal asymptote. This line is the vertical asymptote. This line is horizontal asymptote. Asymptotes means the curve will get very, very close to the line, but never touch the line. Those are called asymptotes. Now, here, we add 2 to x first, and then add 1 to the entire function. So we take 2 steps. In order to get a function, we take 2 steps. First step, when I add 2 to x, I shift the graph 2 units to the left side. First step, when I add 2 to x, I shift the graph 2 units to the left side. So I shift the graph 2 units to the left side. I get y equal to 1 over s plus 2. Shift the graph 2 units to the left side. I get this graph here. It was 0. If I shift it 2 units to the left side, it becomes -2. And when I shift the graph, asymptotes shift at the same time. Asymptotes will be shifted at the same time. When I shift the graph, the asymptotes will be shifted at the same time. This is the vertical asymptote. It was 0 here. If I shift it 2 units to the left side, it becomes x equal to -2. If I shift it 2 units to the left side, it's a -2 here. And the graph stays the same. That's the graph of this function after I shift 2 units to the left side. Next, when I add 1 to the function, I shift the graph 1 unit upward. When I add 1 to the function, I shift the graph 1 unit upward. Shift the graph 1 unit upward. So shift this graph 1 unit upward. When I shift the graph upward, vertical asymptote stays the same. It's still here at -2. That's the vertical asymptote. But the horizontal asymptote, it was 0 originally. If I shift it 1 unit upward, it becomes 1. Horizontal asymptote, it was 0. When I shift the graph 1 unit upward, it becomes 1. Then the graph stays the same. The graph stays the same shape. That's the graph of this function. Next, we need to find the X and Y intercepts and asymptotes. For the asymptote, we know that the vertical asymptote is s equal to -2 because it goes to -2 in the x-axis. Horizontal asymptote is y equal to 1 because it goes to 1 in the y-axis. Those are the asymptotes. Next, let's find the intercepts. Find the S and Y intercepts. The graph will get very, very close to the asymptote. Next, let's find S and Y intercepts. That's the S-intercept, that's the Y-intercept. Let's find S and Y intercepts. So for S-intercept, we set y equal to 0, then solve for x. For S-intercept, set y equal to 0, solve for x. If I set y equal to 0, this function equal to y. If I set y equal to 0, I get 0 equal to 1 over s plus 2 minus plus 1. Solve this equation for x. I can first of all subtract 1 from both sides. I get -1 equal to 1 over x plus 2. -1 can be rewritten as -1 over 1. Then I can cross multiply. I get -x plus 2 equal to 1. Cross multiply. Then I can distribute negative sign. I get -x minus 2 equal to 1. Add 2 to both sides. I get -x equal to 3. Then I can divide both sides by -1. I get s equal to -3. So S-intercept is -3 here. S-intercept is -3 here. S-intercept is -3 here. For the Y-intercept, let me put it here. For the Y-intercept, we set s equal to 0. For the Y-intercept, set s equal to 0. If we plug in 0 for x, y equal to f of 0, which is 1 over 0 plus 2 plus 1. 0 plus 2 is 2, so I get 1 over 2. 1 over 2 plus 1 is 3/2. So the Y-intercept here is 3/2. That's the S-intercept, that's the Y-intercept, and that's the horizontal asymptote, that's the vertical asymptote. Horizontal asymptote, vertical asymptote. That's the graph of this function. Part D, f of x equal to -square root of x plus 3. In order to graph this function, let's choose a parent function first. So for the parent function, usually we drop all the numbers. If I drop number 3 and negative sign, I get square root of x. So I can use f of x equal to square root of x as a parent function. And we need to memorize this graph. So here, for the parent function, we choose the function y equal to square root of x. For the parent function, I choose the function y equal to square root of x. We try to use this function as a reference to graph this function. So try to use the parent function as a reference and graph this function here. First of all, we need to memorize the graph. Square root of x, its graph looks like this. That's f of x equal to square root of x. It terminates at 0. Then we use the parent functions as a reference to graph this function. So So first step, when I add negative sign in the front, when I add negative sign in front of a function, I flip the function over the x-axis. When I add negative sign in front of a function, I flip the function over the x-axis. So first step, flip the function over the x-axis. First step, when I add negative sign in the front, I flip the function over the x-axis. When I add negative sign in front of the function, I flip the graph over the x-axis. So if I flip over x-axis, this point 0 stays the same. If I flip this graph over the x-axis, it looks like this. When I add negative sign in front of a function, I flip the graph over the x-axis. Next, when I add 3 to the function, I get negative square root of x plus 3. When I add 3 to the function, I shift this graph 3 units upward. Shift this graph 3 units upward. Here, this point is 0. If I shift it 3 units upward, it becomes 3. Say 3 is here, for example. Shift this graph 3 units upward. So shift this graph 3 units upward. That's what I get here. Next, we need to label the X-intercept and the Y-intercept. Here, Y-intercept is 3. Y-intercept is 3, we can clearly see it here. But what's an X-intercept? What's an X-intercept? So for an X-intercept, we set y equal to 0. Plug in 0 of y, solve for x. I get 0 equal to negative square root of x plus 3. I can add square root of x to both sides, which is square root of x equal to 3. Next, I can square both sides. I get square root of x squared equal to 3 squared. So square cancel square root with s by itself. 3 squared is 9. So s equal to 9. S-intercept is 9. That's the Y-intercept. That's an S-intercept. So that's a graph to this function. Part E. Graph of function f of x equal to 2x to the power 3 minus 4. Graph this function. First step, we need to choose a parent function. In general, for the parent function, we drop all the numbers. If I drop 2 in the front, drop 4 in the back, what's left is x raised to power 3. So here we can use x raised to power 3 as a parent function. We need to memorize the graph of these special functions. F of x equal to x to the power 3. The graph looks like this. to memorize the graph for these special functions. So we choose the parent function to be y equal to s to the power 3. Memorize the graph. It looks like this. Now, let's use the parent function as a reference and graph this function here. Here, when I multiply 2 to the function, we stretch this graph vertically by a factor of 2. When I multiply 2 to the function, we stretch the graph vertically by a factor of 2. So stretch vertically by a factor of 2. The new function is y equal to 2s cubed. When I multiply 2 to the function, I stretch the graph vertically by a factor of 2. In general, for this graph, if I stretch the graph vertically, it becomes narrower. If I stretch the graph by a factor of 2, if I pull the graph, it becomes narrower. If I stretch the graph by a factor of 2, if I stretch the graph vertically, it becomes narrower. The graph becomes narrower. The curve becomes narrower. If I stretch the graph vertically by a factor of 2, the graph becomes narrower. If I stretch the graph vertically, if I pull these two edges, it becomes narrower. The graph becomes narrower. So that's the graph y equal to 2s cubed. Next, when I subtract 4 from the function, we shift the graph of the function 4 units downward. So I get 2x cubed minus 4. When I subtract 4 from the function, I shift the graph 4 units downward. Y equal to 2s cubed minus 4. For this function, if I subtract 4 from the function, I shift the graph 2 units downward, 4 units downward. Shift the graph 4 units downward. This point, it was 0 originally. When I shift the graph 4 units downward, 0 becomes negative 4. 1, 2, 3, 4. 0 becomes negative 4. The graph stays the same shape. So here we see that the y-intercept is negative 4. What's the s-intercept here? Y-intercept is negative 4. What's the s-intercept? So for the s-intercept, we set y equal to 0. For the s-intercept, we set y equal to 0. So let y equal to 0. I get 0 equal to 2s cubed minus 4. Next, solve the equation for x. Here I can add 4 to both sides. I get 4 equal to 2s cubed. Next, I can divide both sides by 2. I get 2 equal to s cubed. In order to get s by itself, I can take cube root. So I get cube root of 2. S equal to cube root of 2. That's an s-intercept. It's cube root of 2. That's an s-intercept. That's a y-intercept. And this is a graph of this function. Next, how do we graph the function? F of x equal to absolute value of 1/3 of x minus 1. How do we graph this function? First step, Let's choose the parent function first. When we choose the parent function, usually you can drop all the numbers. If we drop number 1, and if we drop 1/3, what's left is absolute value of x. So I choose the parent function to be y equal to absolute value of x. The graph of absolute value of x is a V shape. We need to memorize these special graphs. The graph of this parent function is a V shape. That's the graph of its parent function. Now, when we multiply 1/3 to x, when we multiply 1/3 to x, here 1/3 is less than 1. If 1/3 is less than 1, we stretch the graph horizontally by a factor of 1 over 1/3, which is 3. So, when we multiply 1/3 to x, stretch this graph horizontally by a factor of 3. 1 over 1/3 is 3. So stretch this graph horizontally by a factor of 3. 1 over 1/3 is 3. So stretch the graph horizontally by a factor of 3. If I stretch the graph horizontally, I make it whiter. I make the graph whiter. The graph becomes whiter. If I stretch the graph horizontally, it becomes whiter. Stretch the graph horizontally by a factor of 3 means I make it whiter. That's the graph y equal to 1/3 of x. Next, when I subtract 1 from the function, I shift the graph 1 unit downward. When I subtract 1 from the function, I shift the graph 1 unit downward. So for the graph y equal to 1/3 of x minus 1, we shift the graph 1 unit downward. Shift the graph 1 unit downward. So shift this graph 1 unit downward. This point, it was originally 0. The vertex here was originally 0. If I shift it 1 unit downward, 0 becomes -1. If I shift the graph 1 unit downward, 0 becomes -1. So that's the y-intercept. That's the y-intercept. What's an x-intercept here? What's an x-intercept here? This is the y-intercept, -1. What's an x-intercept here? For an x-intercept, usually we set y equal to 0. So let y equal to 0. I get 0 equal to absolute value of 1/3 of x minus 1. Here I can add 1 to both sides. I get 1 equal to absolute value of 1/3 of x. If absolute value of 1/3 of x equal to 1, that means what's inside must be plus or minus 1. If absolute value of 1/3 of x equal to 1, that means what's inside must be plus or minus 1. So what's inside must be either plus or minus 1. The inside must be either plus or minus 1. Next, we try to get x by itself. So I can multiply both sides by 3. If I multiply the right side by 3, I get x by itself. 3 cancels 1/3. On the left side, if I multiply 1 by 3, I get 3. So x is either plus or minus 3. If I multiply 3 to both sides, x is either plus or minus 3. And we know that this point here must be -3. this point here must be positive 3. So those are the X-intercept, this is the Y-intercept. That's the graph of this function. That's the graph of this function. Next, how do we graph the function? F of x equal to half of cube root of x minus a. Half times cube root of x minus a plus 2. How do we graph this function? F of x equal to half times cube root of x minus a plus 2. In order to graph this function, let's choose the pattern function first. In general, when we choose the pattern function, drop all the numbers. If we drop 2, drop half, drop negative a, what's left is the cube root of x. So we choose the cube root of x as a pattern function. The graph of cube root of x looks like this. We need to memorize those special functions. The graph of cube root of x looks like this. So we use this graph as a reference. Here we use this graph as a reference to sketch a graph for this function. So first step, we're going to multiply half to the function. When I multiply half to the function, I shrink the graph vertically. I shrink the graph vertically by a factor of half. When I multiply the function by a half, when we multiply the function by a half, we shrink the graph by a factor of half. Shrink the graph vertically by a factor of half. So if I shrink the graph vertically, the graph becomes narrower. If I shrink the graph vertically, the graph becomes narrower. If I shrink the graph horizontally, if I shrink the graph vertically by a factor of half, the graph becomes narrower. Next, when I subtract a from x, I shift the graph a units to the right side. If I subtract a from x, I shift this graph a units to the right side. When I subtract a from x, I shift the graph a units to the right side. Shift a units to the right. This point equals 0. If I shift a units to the right, it will be a here. If I shift a unit to the right side, it will be a here. Next, when we add 2 to the function, we shift the graph 2 units upward. Next, shift the graph 2 units upward. When we add 2 to the function, shift the graph 2 units upward. If I shift the graph 2 units upward, I get a function y equal to half of cube root of x minus a plus 2. When I add 2 to the function, I shift the graph 2 units upward. Now let's graph the function. This point is a. If I shift it 2 units upward, somewhere here, shift the graph 2 units upward. Next, let's find the X-intercept and the Y-intercept. Here we have X-intercept here and the Y-intercept here. Let's find the X-intercept and the Y-intercept. For X-intercept, usually we set y equal to 0. So plotting 0 for y, solve for x. We get 0 equal to half times cube root of x minus a plus 2. Solve this equation for x. I try to eliminate the fraction first, so I can first of all multiply both sides by 2. If I multiply both sides by 2, 0 times 2 is 0. 2 times half can cancel. I get cube root of x minus a. 2 times 2 is 4. Next, I can subtract 4 from both sides. I get negative 4 equal to cube root of s minus a. Then I can cube both sides. Cube will cancel cube root. Cube both sides. Cube here will cancel cube root. Negative 4 cube means negative 4 times negative 4 times negative 4, which is negative 64. Cube cancel cube root, we get s minus a. Next, I can add a to both sides. If I add a to both sides, I get s by itself on the right side. On the left side, negative 64 plus a is negative 56. So X-intercept is negative 56, somewhere here. Now next, let's find the Y-intercept. For the Y-intercept, we set y equal to 0. For the Y-intercept, set x equal to 0. For the Y-intercept, set x equal to 0, solve for y. For Y-intercept, set x equal to 0, plotting 0 here, and find y. Y equal to f of 0, which is half of cube root of 0 minus a plus 2. 0 minus a is negative a. Cube root of negative a is negative 2, because negative 2 times negative 2 times negative 2 is negative a. So cube root of negative a is negative 2. Half times negative 2 is negative 1. Negative 1 plus 2 is positive 1. Negative 2 plus 1 is positive 1. So the Y-intercept is positive 1. Y-intercept is positive 1 here. That's a graph of this function. That's a graph of this function. Next example, f of x equal to 4 over x plus 3 squared minus 1. How do we graph this function? Let's choose the parent function first. In order to choose the parent function, let's drop all the numbers. If we drop number 1, drop number 4 on the top, drop number 3 on the bottom, it looks like the parent function is y equal to 1 over x squared. So we can choose this function as a parent function. And the graph of this function looks like this. The graph of f of x equal to 1 over x squared looks like this. We choose this function as a parent function. In general, we need to memorize the graph of these special functions. So that's the graph of this function, y equal to 1 over x squared. It looks like this. In this graph, there are two asymptotes. This line is the vertical asymptote, which means the curve will get very, very close to this line, but never touch this line. And this line is the horizontal asymptote. This line is a horizontal asymptote. The curve will get very, very close to this line, but never touch this line. So use this graph as parent function. That means use this graph as a reference and graph this function here. So first of all, let's take care of number 4 on the top. How do we make 4 on the top? If we try to make 4 on the top, I can multiply this function by 4. If I take 4 times this function, I can make 4 over s squared. That's how we make 4 on the top. If there's a 4 on the top, we multiply this function by 4. If I multiply a function by 4, I stretch the function vertically by a factor of 4. So stretch the function vertically by a factor of 4. Stretch this function vertically by a factor of 4. Stretch the function vertically by a factor of 4. If I stretch this function vertically, the curve gets further away from the x-axis. If I stretch this graph vertically, the curve gets further away from the x-axis. If I stretch the curve vertically, the curve gets further away from the x-axis. When we stretch the function vertically, the asymptote stays the same. This is vertical asymptote, and this is horizontal asymptote. When we stretch the functions, its asymptote stays the same. Next, when we add 3 to x, we shift the graph 3 units to the left side. When we add 3 to x, we shift the graph 3 units to the left side. When we add 3 to x, stretch the curve, shift the curve 3 units to the left side. Shift this graph 3 units to the left side. When we add 3 to x, shift this graph 3 units to the left side. So shift the graph 3 units to the left side. It was 0 here. If I shift the graph 3 units to the left side, it becomes -3. So that's the new vertical asymptote. When I shift the graph 3 units to the left side, that's the new vertical asymptote. When we shift the graph, we need to shift the asymptotes at the same time. That's the new vertical asymptote. Then the graph stays the same. And horizontal asymptote stays the same. Next, when we subtract 1 from the function, we shift the graph 1 unit downward. When we subtract 1 from the function, shift the graph 1 unit downward. Shift the graph 1 unit downward. So when we shift the graph downward, vertical asymptote stays here. At -3. horizontal asymptote, if I shift it downward, it will be -1. Originally, it was 0. If I shift it downward, it becomes -1. If I shift it downward by 1 unit, it becomes -1 here. That's the vertical asymptote. This is the horizontal asymptote. This is the vertical asymptote. So horizontal asymptote is -1. Vertical asymptote is -3. Then sketch the graph in the same shape. It's the graph y equal to 4 times x plus 3 square minus 1. So that's the graph. Next, let's find the asymptote. This asymptote is vertical asymptote s equal to -3. This asymptote is horizontal asymptote y equal to -1. Those are the asymptotes. And then next, find the intercepts. Find the X-intercept and the Y-intercept. Find the X-intercept and the Y-intercept. So for X-intercept, for the X-intercept, we set y equal to 0, which means plotting 0 for y, solve for x. Set y equal to 0, solve for x. We have 0 equal to 4 over x plus 3 square minus 1. We try to get x by itself. So I can first of all add 1 to both sides. I get 1 equal to 4 over x plus 3 square. Then this number 1 can be rewritten as 1 over 1. Then I can cross multiply. If I cross multiply, I get x plus 3 square equal to 4. Next, I can take square root on both sides. When I take square root, x plus 3, it could be either positive or -2. When I take square root, x plus 3 could be either positive or -2. Then solve for x. Here, x plus 3 could be either positive 2 or it could be -2. x plus 3 here could be either positive 2 or -2. If it's positive 2, I subtract 3 from both sides. I get s equal to -1. If it's -2, I subtract 3 from both sides. S is -5. So X-intercept is either -1 or -5. So this is -1. This is -5. Those are the X-intercept. Next, let's find the Y-intercept here. Next, let's find the Y-intercept here. For the Y-intercept, we say s equal to 0. Then plug in 0 for x, find y. Y equal to f of 0. If I plug in 0 for x, I have 4 over 0 plus 3 square minus 1, which is 4 over 3 square minus 1. 3 square is 9. The number 1 can be written as 1 over 1. And then find the least common denominator. Here, least common multiple is 9. So in the second fraction, I multiply top and bottom by 9. So I can make 4 over 9 minus 9 over 9. They have the same denominator, keep denominator, subtract the numerator. 4 minus 9 is -5. So the Y-intercept is -5 over 9. Y-intercept is here. -5/9. That's the Y-intercept. -5/9. So that's an X-intercept. That's the Y-intercept. That's the graph of this function. Next example, find the function of the graph after performing the indicated transformations on the graph of the parent function. Part A, the parent function is f of x equal to x squared. We first of all flip the graph over the x-axis. Then we shift the graph 2 units to the left. Find the function of the graph after performing these two transformations. So the parent function is f of x equal to x squared. If I flip the graph over the x-axis, I add negative sign in the front of the function. If I flip the graph over the x-axis, add negative sign in front of the function. If I flip the graph over the x-axis, add negative sign in front of the function, I get negative x squared. Next, shift the graph 2 units to the left. If I shift the graph 2 units to the left, add 2 to x. If I shift the graph 2 units to the left, add 2 to x. So that's the function of the graph after performing both transformations. That's the answer. Part B. The parent function is a function f of x equal to the fourth root of x. We first of all stretch the graph vertically by a factor of 3. Then we flip the graph over the y-axis. Then shift the graph 4 units downward. So let's perform the first transformation first. Stretch the graph vertically by a factor of 3. If we stretch the graph vertically by a factor of 3, we multiply the entire function by 3. If we stretch the graph vertically by a factor of 3, we multiply the entire function by 3. Next, flip the graph over the y-axis. If we flip the graph over the y-axis, add negative sign to the front of x. If we flip the graph over the y-axis, add negative sign in the front of x. If we flip the graph over the y-axis, add negative sign in the front of x. Next, shift the graph 4 units downward. If we shift the graph 4 units downward, subtract 4 from the entire function. If we shift the graph 4 units downward, subtract 4 from the entire function. That's the graph. That's the function of the graph after performing the indicated transformations. That's the function of the graph after performing all these 3 transformations. Next, the parent function is f of x equal to absolute value of x. First of all, shrink the graph horizontally by a factor of half. Next, shift the graph 2 units to the left, to the right. Then shift the graph 3 units upward. Let's perform these operations. First of all, shrink the graph horizontally by a factor of 1/2. If I shrink the graph horizontally, I multiply some number to x. If we shrink or stretch the function, if we shrink or stretch the graph horizontally, we multiply a number to x. For horizontal stretching and shrinking, we multiply a number to x. If this number is greater than 1, we shrink the graph. If it's less than 1, we stretch the graph by a factor of 1 over c. Always shrink or stretch by the factor of 1 over c. Here, we are stretching and shrinking by the factor of 1 over 2, which means 1 over c is 1 over 2. If we cross multiply, you can see that c equal to 2. So I get absolute value of 2x. If we shrink horizontally by a factor of 1 over 2, we multiply the reciprocal 2 to x. Since 1 over c is 1 over 2, c by itself is 2. So we take 2 times x. When we string the graph horizontally by a factor of half, take the reciprocal times x. Next, shift the graph 2 units to the left, to the right. When I shift the graph 2 units to the right, I subtract 2 from x. When I shift 2 units to the right, I subtract 2 from x. Subtract 2 from x, not to 2x. We cannot write 2x minus 2. This is, we subtract 2 from 2x. We must directly subtract 2 from x. So take 2 parentheses x minus 2. When we shift the graph 2 units to the right, subtract 2 from x. Subtract 2 from x directly, not from 2x. So we need to add parentheses. Subtract 2 from x directly, not from 2x. If we don't add parentheses, it means we subtract 2 from 2x. But we must subtract 2 from x directly. So add parentheses. Subtract 2 from x directly. Shift 2 units to the right. Next, shift 3 units upward. If I shift the graph 3 units upward, I add 3 to the entire function. Add 3 to the entire function. If we shift the graph 3 units upward, add 3 to the entire function. That's the function of the graph after performing indicated transformations. That's the function of the graph. Part D. The parent function is a function f of x equal to 1 over x. First of all, stretch the graph vertically by a factor of 4. Next, flip the graph over the y-axis. Next, shift 5 units to the left, and then shift 4 units downward. So let's perform operation here. First of all, stretch the graph vertically by a factor of 4. If I stretch the graph vertically by a factor of 4, means I take 4, multiply to the entire function. If we stretch the graph vertically by a factor of 4, that means we take 4, multiply to the entire function. That can be rewritten as 4 over x. This can be rewritten as 4 over x. Next, flip the graph over the y-axis. Flip the graph over the y-axis. If we flip the graph over the y-axis, we make x to be negative x. If we flip the graph over the y-axis, add negative sign in front of x, make x to be negative x. Next, shift the graph 5 units to the left. When we shift the graph 5 units to the left, we add 5 to x. Add 5 to x directly. That means do negative x plus 5. Add 5 to x, not add 5 to negative x. If we don't add parentheses, that means we add 5 to negative x. Here, when we shift 5 units to the left, we need to add 5 to x directly, not to negative x. So here we need to add parentheses. Add 5 to x directly. Next, shift the graph 4 units downward. If we shift the graph 4 units downward, we subtract 4 from the entire function. Subtract 4 from the entire function. That's the function of the graph after performing indicated transformations.